Hello everyone and welcome to a new open class. Welcome back to these great classes that we are doing weekly. So yeah, welcome everybody. Today we are going to be doing class number 205, and the topic for today's class is going to be quaternions, right? So that is especially I remember when I was starting or just getting started in the robotics world. Yeah, quaternions was one of the trickiest things for me to understand. So probably for some of you it's the same case. So yeah, today we are going to try to introduce this concept of quaternions, which is very important in robotics. Try to explain it as easy as possible and see some ways of reading these quaternions from the robot, also visualizing them, trying to track issues that can happen when working not with quaternions but with regular Euler angles. So yeah, let's go for it. Then hello everybody. Let me know as always, please, if everything is good. If the audio is good, the video is good. I'm going to checking the chat for any feedback from your side. So yeah, let me already get started. Then I'm going to start sharing my screen right now. There we go. And I'm going to log in so that I can have access here to the chat. Where do we have the class? Here, okay. There we go. All right, so I can see all of you here already. From Virginia, from Mexico, from Spain, from Washington. All right, so we have a quite international class. So yeah, hello everybody and welcome. Then I don't know if you are already veterans of these open classes. I can recognize some names there in the chat which are very familiar, but maybe some of you are also new to these open classes. So let me tell you that for our open classes, we always do them interactive, okay? So this is not a class where I'm going to be here explaining things and showing some things to you, and you sit there just listening and watching to what I am saying and what I am doing. That's not the case, all right? So in our classes, we always like to get you involved. So for this, we have prepared a ROSJECT, okay? A ROSJECT is basically an online ROS-based project, okay? That can be run directly from a browser without any other installation. And you might be asking, okay, Alberto, very nice, but how do I get this project? Okay, it's very easy. All you have to do in order to get today's class project is to click on this button that appears here right above the chat, which says fork and open the class project. All right, I'm going to click here myself to get my copy of the ROSJECT for today's class. And then once you click on this button, a couple of things are going to happen. Yeah, first of all, you are going to be redirected, as you can see here, to the main ROSJECT page. Here it's still loading. It might take a few seconds to fully load. And then here in the right side, you have the stream panel, let's say, with the video feed, the chat, so that you can post your comments, questions, etc. All right. In my case here, I'm going to just move this out of my ROSJECT page so that I can have more space and you can see better what's going on here in my screen. All right. And then what I will just do is to open the chat here in another page so that I can still read you. All right. Then this is first thing, okay? So once you click here, you're going to be redirected to the main ROSJECT page. Then let me also tell you that while doing this, you are also getting a copy of this ROSJECT for your account, okay? And this copy is permanent. What does this mean? This means that whenever you access your deconstruct account and then you come here to the My ROSJECTs section in the left menu, yeah, whenever you come here to the My ROSJECT section, you are going to be able to find here this ROSJECT and open it to continue working on it or whatever you want to do with it, but you are going to have this copy forever. Okay, so all these ROSJECTs that you get from the classes are permanently here in your account. All right. Okay, then yeah. So my ROSJECT is almost loaded. So I'm going to wait here until it fully loads. There we go. It is loading right now. Then let me close all these because probably for you, when you open the ROSJECT for the first time, you are going to have only the notebook appear, okay, like this, and also the terminal, which does some basic installations here, automatic installations, all right? So, yeah, once your ROSJECT finishes loading, you are going to see something like this, yeah, where you have the notebook, which contains basically all the explanations, images, example codes, everything that we are going to be doing during today's class. Everything you can find it here in the notebook, in the ROSJECT notebook, all right? And then also we have a terminal here that has automatically opened that we are going to be using. This is a regular Linux terminal, okay, where you can just type commands like in a Linux computer, in a Linux machine, all right? So let me know, has everybody been able to get and open their ROSJECT? Any issues so far? Are we good to go? Hello from Buenos Aires, says Franco. From Sri Lanka, we have Kushan also. Yeah, so has everybody been able to open the ROSJECT successfully? Yes? Okay. I don't see anybody complaining in the chat, so that usually means that everything is fine. Okay? All right, then let me continue. I will keep reading the chat in case there's any problem. All right. Then, yeah, so let's already get started with the class, right? Then today we are going to cover the topic of quaternions in robotics, okay? Very important topic, tricky to understand clearly, especially as a beginner. Then the main goal for today's class is going to be basically to try to clarify a little bit this concept of quaternion, and more specifically in the field of robotics, yeah? So as in the last classes, we are going to be working with the BotBox warehouse kit, okay, which is our kit, our robotics kit for educational purposes, where basically you are going to receive an already made project, okay? Let's say a physical environment, okay? Those are better words, yeah? You are going to get 3 robots with an already built environment for you that is especially designed for educational purposes, yeah? And for practice-based robotics. Okay, everything is already prepared, so it requires minimal preparation and maintenance, and it's also very easy to assemble. Okay, then besides all the physical kit, you are also going to receive already prepared ROSJECTs and many more things. So in case that you are interested in something like this, I have left here the link so that you can get more information about this BotBox Warehouse Lab, and you can get yours and start teaching robotics very easily, okay? Both in simulation and in hardware, which is the best way to teach robotics as we think at the construct. All right, then let's get started. So, what are quaternions? Yeah, are you guys? Let me start by asking here you in the audience. Are you familiar with quaternions? Do you know what they are? Have you worked previously with them? Do you have no idea of what quaternions are, or maybe you have heard the word quaternion, but you are still a bit confused? So, how is that concept for you right now? Just to have a better idea of your background. Okay, I am seeing here my second computer that I have here at the left side, and it seems like the chat here is freezed. Okay, so let me refresh it, because it's not refreshing. Okay, there we go. Now I can see. Okay, so these are all the answers from the project loading phase. So I can see everybody was good to go. The ROSJECT button is grayed out for me. If you mean this one, Win, try refreshing the page. Okay, maybe that does the trick. Try refreshing and it should show like this. It should be clickable, okay? Yeah, this is for Win. I've heard of them, but don't understand them, says Joel. Okay, it is for numbers. Okay, heard of them, no experience. Something to do with orientation, says Vishal Deka. Yes, you are on the right path, Vishal. No experience, orientation, representation. That is better than Euler angles. Okay, so Tafarel, I see that he knows what he's talking about already. Just heard, represent a rotation with a vector with 4 elements, 3D complex space that moves around, and the 4th dimension of a space is the real number system. It is used in navigation and movement. Heard of them, no technical experience. Complex number with 3 imaginary parts, mathematical concept for 3 rotation. No experience, no idea about it. Okay, so we have a bit of everything, right? Okay, then, yeah. Lots of you I see that you have already an idea of what this is, but basically, quaternions are a powerful mathematical tool used to represent 3D rotations, or what is the same, to represent rotations or orientations in the 3D space. Okay? And I also saw a comment which says something like that. They provide a robust way to handle orientations. And by robust, I mean better than other approaches, okay? So it is robust. Why? Because it avoids pitfalls such as the gimbal lock, okay? Which we are going to see later, what specifically this gimbal lock means, yeah? Which can occur when using other traditional methods like Euler angles, yeah? Euler angles, probably most of you are familiar with them, yeah? Roll, pitch, yaw. They can be represented with degrees, with radians, etc. Yeah, it's the most common way. Yeah, the thing is that Euler angles are not very good at keeping track of orientations, of complex orientations, let's say. Okay. Yeah. So when we have to build applications where smooth and continuous rotations are required, for example, robotic arms, as we can see here, drones, autonomous vehicles, etc. Yeah. So for these kind of scenarios, which are very frequent in robotics, quaternions are much more robust and also efficient, by the way, than Euler angles. Okay. So this is why quaternions are very important in robotics, okay? Because they allow us to represent rotations, orientations in the 3D space, okay? So why we use quaternions? For several reasons. The ones that we have described, yeah? Also smooth interpolation, yeah? So it facilitates smooth transitions between orientations. Yeah. So we are going to see also an example of this later during the class, a practical example. It is also more robust than working with Euler angles because it avoids singularities, for example, the Gimbal lock that we were mentioning. Yeah. And also it is more efficient. Yeah. So computationally, they are more efficient. Okay. And some real-world examples that use quaternions and where quaternions are crucial, are very important, yeah, are, for example, robotic arms, huge topic, drones, okay? These are the two most common examples of robots that can, let's say, rotate in the 3D space, okay? Robotic arms and drones. And also for autonomous vehicles, yeah, especially for navigation systems. All right. Okay. Then, having done the proper introductions, let's start getting into a bit more of practice. Okay. I don't like to talk a lot without doing things. You already know me. So let's start already with some practice, okay? Then we are going to start by launching our simulation and executing a basic program to visualize the orientation in quaternions, okay? Then here we have the program that we are going to be executing. It's a very basic Python program. So first of all, let's create it. Okay, then in order to create the file, you can create it with the terminal, with the touch command, for example. It's what I am doing here. Or if you prefer, you can also do it using the code editor, okay? Here inside the ROSJECT, you have terminals, but you can also open a code editor, yeah? In order to do so, you can click on the icon here, which is at the right side of the terminal icon. Yeah, it says code editor. Then if you click here, this is going to open the code editor, which is going to allow you to see and manage all the folders, files, etc. of this ROSJECT with a graphical environment, which is always better. Yeah. Then in this case, we are going to be working inside the ROS2 workspace. Okay, here is where we are going to be placing the files. So for example, let me do this first one following the commands here in the terminal. So I'm going to just copy these two commands directly here from the notebook by pressing here in the copy button. And then I can come back here to the terminal and paste the commands. Okay? And then suddenly now here I have created this new Python file, bis underscore orientation. Okay? Then, for example, now you can double click this file and obviously it's going to be empty. So the next step is going to be to actually copy and paste the code that is shown here in the notebook to the file, okay? So let me copy it and paste the code directly here to the file. All right. Then, now that we have our file, before being able to execute it, what we are going to do is to have some kind of robot available, yes? Because we always want to apply this to robotics. So let's launch our bot box simulation, yeah? The environment that I was introducing earlier, yeah? We are going to be working with a simplified simulation of that environment, yeah? And in order to start this simulation, you have the commands here also, yeah? Here you have the commands to launch the simulation, yeah? Actually, it's 3 commands. You can copy them all together or separate, it doesn't matter. The first one, let me go one by one, just to explain what they do. It's very simple. Then, well, we can do it here or we can open a new terminal, okay? It doesn't really matter. So, in this case, I'm going to leave this first terminal here without running the simulation because I'm going to be later executing the Python program in this first one, okay? Then I'm going to open a second terminal here, yeah? By pressing in this button, create new terminal. And then, as you can see, this opens a new terminal. And I'm going to take just a second to rename this tab to simulation so that I know that here I have the simulation, okay? Then, yeah, so this first command is just a script to kill any previous running Gazebo processes, okay? So you just execute it, and this is going to kill any Gazebo process. Okay, then we source the proper ROS to workspace with the second command, where we have all the simulation packages. It's this simulation workspace. So we need to source it. And then third and last is the ROS to launch command to actually bring up the simulation environment. Okay, this is going to start Gazebo, spawn the robot, spawn the environment, etc. into Gazebo. Okay. So after a few seconds, as you can see, you should see automatically pop up here a Gazebo window, which is going to show the simulation, okay? Then sometimes the first time that you try to launch the Gazebo simulation, it's not going to work, okay? Here I can see already that I'm not sure if this environment is going to work. No, it seems like it's dead, okay? Why I know this? Well, basically a couple of things. First of all, I'm trying to zoom in the environment and it's not responding, right? I am trying to rotate also the view in Gazebo and it's not responding, okay? So if this happens, don't panic, okay? No worries. It happens with Gazebo sometimes. Then if the simulation is not properly working for you, just Control-C in the terminal where you started the simulation, okay? You wait a few seconds until it dies. You are going to see that probably the simulation is going to still appear here because this is actually dead, yeah? Then what you need to do is to run again the clean Gazebo script, okay? You execute again this clean Gazebo script, and this is going to make sure that Gazebo, the Gazebo processes are killed, and then once they are killed, you can execute again the ROS to launch command to bring up the simulation, okay? And then this second time is going to start properly. Here you will see. See, so now I get the proper view, so I can, for example, I can zoom in the robot, I can rotate the view, all right? So now the simulation is working properly, okay? Yeah? So far, so good. Has everybody been able to launch the simulation? Any problems with that? All good. It is working. Simulation launch. Okay. Okay, excellent. Then we are good to go. All right, so first step is to start the simulation. Second step is to execute our Python program, right? Then, before actually executing the program, we can have a quick look here at what is this supposed to do, right? So, this is a quite simple Python program, okay? So, we have some imports here of some classes that we need to do, some libraries, like for example, matplotlib to generate a plot. Yeah. Then here we are creating our Python class, which is named Quaternion Visualizer. Yeah. Then we have our constructor. In the constructor, the most important thing is this part here. Yeah. What we are doing here? Here we are defining a ROS subscriber. Okay, a ROS2, indeed, this is ROS2, okay? So we are defining a ROS2 subscriber. And we are subscribing to the ODOM topic, okay? The ODOM topic is the typical topic that is used in ROS for tracking the odometry data of the robot, yeah? And the odometry data of the robot contains, among other things, information about the position and the orientation of the robot. Yeah? The position is tracked in a regular XYZ. Yeah? And the orientation is tracked using quaternions. Yeah? So we can, for example, have a look at this odometry message, which is the message used in the ODOM topic. Yeah. For example, I can do ROS2 interface show nav sorry, I need to change my keyboard to span. There we go. Messages, and then odometry. Okay, this command is going to show me the structure of the odometry message. Oh wait, I need to put here message, right? Yeah, there we go. Okay, so this is going to show me the structure of the odometry message used in ROS systems. Yeah, and as you can see, it contains many fields, but this is the one which we are more interested in. Yeah, this part of the message, the pose, as you can see, is the estimated pose that is typically relative to a fixed world frame. Yeah, and this pose has basically two components: the position, which is represented in X, Y, Z coordinates, and the orientation, yeah, which is, as you can see here, a quaternion. Okay? Yeah? Then this is going to provide me the orientation of my robot in a quaternion format. Okay? So this is why here in my program I am subscribing to this ODOM topic. Okay? Then here I am just initializing the plot. Right? Here I have the callback function for my subscriber. Yeah. So every time a new message is published into the ODOM topic by my robot, this callback function is going to be triggered. Yeah. And in this callback function, what I am doing basically is to get the orientation from the odometry message. Yeah. So from my odometry message, I am accessing and saving the orientation part of the message into this orientation variable, okay? And then here I am keeping track of the last orientation, okay? As you can see, I am extracting the 4 components. Yes, some people already mentioned in the chat that it's 4 numbers, one part is a real number, another part is imaginary. We are going to see that in a moment, okay? But we can see that we are saving 4 numbers here in the orientation, which is the quaternion, okay, representing the orientation. Okay, and then we have a helper function here to update the plot, keep updating the plot, and another function here to destroy the plot. Once we kill our program, we stop our program, okay? Then, all right. So very simple program where we get the odometry information from the robot. We specifically get the orientation information, which is in quaternion format, and then we are plotting this value. Yeah, we are plotting this quaternion, the values from X, Y, Z, W. Yeah. So let me then execute my program here. I'm going to execute it in the first terminal. Yeah. So let's execute it with the command here again. Yeah, you have all the commands in the notebook. So Python 3 and the name of the file. Okay, and then after a few seconds, again, you are going to see a new window appearing. Yeah? Here I have the plot which is being generated by my program. Yeah? You can see here 4 components, X, Y, Z, and W. Okay, but only we have some values in Z and W. Yeah, you can see here they are around 0, 7. Z and W. For X and Y, they are 0. Okay, or almost 0. All right. Then what can I do now? Okay, let me start moving a little bit the robot. Okay, because right now my robot is quiet. Okay. So it's keeping an static orientation, so it's normal that nothing happens here, okay? Then let me start moving a little bit my robot, rotating it, to see what happens with the plot, okay? Then for this, we can use a very well-known program in ROS and ROS2, which is the teleop twist keyboard, okay? This program, as probably most of you know, allows you to move the robot, to send velocities to the robot using the keyboard. Yeah? So I'm going to copy this program and I'm going to open a 3rd terminal, okay? I need 3 terminals. First one is running my Python program, yeah? Second one is running my simulation, And then I'm going to open a third one where I'm going to execute the teleop. And actually, I'm going to rename it also to teleop to know that here I have the teleop. Okay, then let me run the teleop program. And now let me rearrange a little bit, all this. So let me put my robot here so that I can see how it's moving, how it's rotating. Let me put it here, there we go. And let me add some space here to visualize the plots. Okay, and then let me close this a little bit. All right, so here I can see the plots, and I can see also my robot here in the right side. All right, there we go. Okay, then I'm going to start rotating my robot, let's say, towards the left. Okay, let's do that. So let me put this here, here, and here. Okay, let me start rotating the robot to the left. You can see how the robot here starts rotating, and you can see here how the quaternion is being modified. Okay? Yeah, so my robot keeps rotating, and you can see here how the quaternion values are changing, but only two values are changing, right? Only the Z and the W values are changing, right? Does somebody know why this is in the chat? Anybody knows why only the Z and W values are changing? By the way, whenever you want to stop the robot, you can just stop the program, okay? And that's it. The teleop program. Does anybody know? No? I'm going to be explaining it anyways, okay? But I want to ask first if anybody has an idea. It rotates around Z-axis with a value, because the robot only rotates on Z-axis. Okay, very well. Very well. Yes, exactly because of that. Yeah? So my robot is only rotating around the Z-axis. Yes? It is a differential drive robot. Yeah? Let me print here the axis of the robot. Yeah? So the Z-axis is the blue one that we have here, right? Yeah? This blue axis that we have here, this is the Z-axis. Okay? Red one is X, and green one is Y. Okay? And my robot, because it is a mobile robot, it moves alongside the floor, etc. Yeah? And it is a differential drive motion. My robot can only rotate around the Z-axis, right? Because of this, the only values that I'm going to see here changing in the quaternion are Z, which is the axis of rotation, and W, which is the scalar, yeah, the real part. Okay? Then, knowing this, let's explain a little bit more what these values are. Okay? So, quaternions extend complex numbers. Yeah? Complex numbers have two components, a real part and an imaginary part. Okay? Then, typically a quaternion can be represented in the following form. Yeah? So quaternion is equal to W plus Xi plus Yj plus Zk. Okay? This is the typical form of representing complex numbers. Okay? Then W is the scalar part of the quaternion, which is the real part of the number, and XYZ is the vector, which is the imaginary part. Okay? So, the scalar part is the W. This is not W, actually. This is how is this named? I think it's omega. Or, yeah. Well, I have my maths a bit rusty, to be honest. Okay. But yeah, without trying to complicate things too much, because maybe some of you don't have this mathematical background of working with complex numbers, etc. basically, yeah, the scalar part, which is the real part of the number, represents how much the robot has rotated, yeah? It's the magnitude of the rotation, let's say, yeah? While the vector part, yeah, which is the imaginary part, represents which axis is the rotation happening around, yeah? So, in our example, yeah, we have our vector represented by x, y, z, yeah? And my robot is only rotating toward, with respect to the z-axis. So this is why I can only see this value being present in my quaternion, in my representation here of the quaternion, okay? And the W, obviously, because this is the magnitude of the rotation, okay? Yeah. Then we have a very interesting. I don't want to get too into details into mathematics, okay? Because I think it's going to be harder, especially for beginners. But you have here some more mathematical representations, okay, of how you can compute the quaternion. But I want to show you this tool, online tool, which is very interesting and can be used to visualize in an easy way quaternions, okay? Then if you click here, this is going to take you to this page, okay? And here, what you can do is to uncheck the animation part, okay? And then this is going to stop. And then here, basically, you can see rotation in two different formats. The quaternion, which is the one that we are here for today's class, right? And the Euler angles, which are the typical one, okay? You can change from degrees to radians or from, and change the order, okay? Now, typically we always, for us humans, it's much simpler, right, to understand Euler angles, right? So for example, in the case of my robot, yeah, I know that if this is my x-axis, this is my y-axis, and this is my z-axis, so if my robot rotates, let's say, 90 degrees in the z-axis, we can see that the rotation is going to be something like this, right? Yeah? So, for example, yes, if my robot is right now here, yeah, and I rotate, let me try to do it like this, yeah, I rotate 90 degrees in the z-axis, it's going to be something like this, right? Yeah? And this is very easy to see in Euler angles, right? For example, if the rotation is 180, then it's going to cover all these, yes? So for example, now if I do another 90 degrees, yeah, the rotation is now 100 degrees, right? This is pretty obvious. But in Euler angles, we can see this clearly, but this can become much more tricky here in when working with quaternions, right? It is not obvious at all, yeah? So this rotation of 180, how it is represented in quaternions, yeah? It's much more tricky when we try to understand or imagine a rotation using only a quaternion, right? Then this is very interesting because, for example, we can start moving here the rotation only from the z-axis, and we are going to start seeing how we get exactly the same value as we were getting in our plot, yeah? So if we change the orientation with respect to the z-axis, we can see how in the quaternion the w and z values are changing, okay? If we had a robot, for example, that could rotate on the y-axis, then that would change, obviously. Yes? See? So now we have w and y. Yeah? And here we are only rotating one angle at a time. Okay? But in more complex systems, we can have simultaneous rotations, yeah? So all the angles can be changing at the same time, yeah, which is this what the animation shows. Yeah, this is for more complex rotations, like manipulator robots, like drones, those kinds of robot which have more degrees of freedom, right? Okay. Omega, yes, that was it. Yeah, RS deep. Okay. Then let's see another example. Okay. Let's continue seeing more examples of quaternions. So, okay, so here we can already stop the program, right? Let me stop the program. And we are going to create a second program, okay? Now we are going to create another program to extract the quaternion from the ODOM topic, okay? So here again, let's just create the file and check what's going on in the program, okay? So let's create this second program. Let me create it again here, ODOM extract, and then copy and paste the code here to the program. There we go. Okay. So, yeah, so what are we doing here? Well, it's very similar, okay? We are just separating the scalar part from the imaginary part, okay? So here what we were doing was to subscribe to odometry, to the ODOM topic, and then extract the orientation, yeah, in Z, Y, Z, W, and then plot individually these values, okay? Now here what we are doing again is subscribing to the ODOM topic, and then here we are separating the scalar part, which is the real part, the omega, from the vector, which is the imaginary part, which represents the axis of rotation, right? Then we can execute this very quickly. Let me come back here to my robot. Okay, then we can execute our program like this. You can restart the simulation if you want. It's not needed, okay? But yeah, in case that maybe you move the robot to the wrong place or it crashed against something, whatever, don't worry, okay? You can always, I'm going to do it just for reference so that you can do it also in case that your simulation breaks or whatever. Don't worry. Just execute the clean Gazebo script to kill all the Gazebo processes, and then just execute again the bring up command for restarting the simulation, okay? No problem at all. That's the good thing of working with simulations, right? That if something goes wrong, we can just restart the simulation and we are good to go. Okay, then let me get closer here to the robot again. And then, oopsie, sorry. Okay. And then here, let me execute the program, ODOM extract. There we go. And then this is going to start printing the values, yeah? So we can see here the scalar value, which is 0.707, and the vector, which again is 0, except for the x-axis, which is 707, more or less, okay? So basically, my current orientation here is 0.707. Wait, let me put all this to 0, 0, 0, 0, and then 0.707 in the z-axis. I don't know why it's not setting properly. Anyways, okay. Okay. Yeah, so it's basically 90 degrees here, right? It's 90 degrees in the yaw axis. There we go. Okay, so we have something like this. Yeah, as you can see. Yeah, let me stop the program for a moment, just so that I can have this fixed. Yeah. So our scalar value is 0.707, and the value of the z in our vector is 0.707, more or less, okay, with a small error. So, introducing this here, we can see that this corresponds to a rotation of 90 degrees. Okay, so my robot is spawned with an initial rotation of 90 degrees. Yeah, with reference to the world frame. This is to the Gazebo world frame. Okay? And then we can then obviously very easily see that if we start rotating our robot, yeah, let's say that we start rotating our robot again using our keyboard teleop, obviously we are going to see how both the scalar and the z value start changing, right? So let me start rotating the robot, and there we go. Okay, we can see here how the values are updating. Again, only the w, the scalar, and the z portion of the vector are changing. Okay, so this is exactly what happens if I do this and then I start rotating my robot around the z axis. Yeah. All right, so this is an interesting tool in order to be able to see quaternion representations, but as we have also the respective Euler angles, it's easier to understand, especially at the beginning. Yes, because we can imagine much easier, we as humans, yeah, we can represent mentally much easier Euler angles than quaternion angles. Okay? Yeah? So let me here again stop the program. And with this example, we are ready to enter the last one, okay? Which is also introducing the concept of gimbal lock. Is somebody familiar with the gimbal lock concept? Or not? Yes, says Arek. Okay. Yes, singularity, says Venus. Yes, exactly. So basically, this is a singularity that happens when we have these kind of systems. Okay? Then in our case, we don't have this, but we are going to see another problem. Okay? Then this is easily seen, for example, in aircrafts, okay? Yeah, so what happens? Here we can see the three axes, yeah, roll, pitch, yaw, yeah, and we have 3 degrees of freedom, yeah? So all them can rotate independently of the other, yeah? Here we can see the roll, right? Here we can see the pitch rotating, which roll is the red, pitch is the green, and here we can see the yaw rotating, which is the blue. Okay? So this system has 3 degrees of freedom, and they can move and rotate at the same time, as you can see here in the image in the right, right? Now here, in the image in the left, we have the singularity. What happens? That when 2 of these axes aligned, for example, here we can see that the green and the red, yes, so roll and pitch, are aligned. Yeah? Then when this happens, their rotations are essentially the same, which means that the system loses a degree of freedom. Okay? Then this is known as a singularity, as Venus was saying, and this can cause problems in this kind of robotic systems if we work with Euler systems, yeah? Euler systems meaning roll, pitch, yaw, okay? Yeah? Then in order to avoid this gimbal lock, yeah, what can we do? Well, use quaternions, yeah? With quaternions, we don't have this problem. Yeah, they allow us to represent these complex systems without having any singularity. Yeah, because if our system falls in a gimbal lock, for example, then we are going to start having strange orientations, okay, and mathematical problems which can become a mess. Okay, so this is why working with quaternions it's essential in robotics. Okay, yeah. Does this make sense? More or less. I know it can be a bit trickier. Okay, but does it make sense? This gimbal lock problem that I explained it. It makes sense. Yeah, you have to think of systems that can rotate in the 3 axes, okay? So for example, our robot cannot rotate in the 3 axes, yes? Our robot can only rotate in the z-axis, as we have seen, but there are other systems like robot manipulators, drones, spaceships, etc., that can rotate in the 3 angles, okay? Yeah. All right. Then let's see something else. Okay. So now we are going to create a third program. Okay. So let's create this third program right now here. So let me create the file, the first terminal, copy the code and paste it. There we go. And then, well, that's it. Yeah, so we have our simulation here running, and then we have the teleop program. Okay, so we are good to go. Then let's have a quick look at this program. What we are doing here? Well, here what we are doing is, again, subscribing to the ODOM topic, right? And then, in our ODOM callback, okay, what we are doing is to get the quaternion from the orientation, but then what I am doing is to convert this quaternion to roll, pitch, yaw, okay? So because I get the orientation in quaternions from the odometry ODOM topic, yeah, what I am doing here is to convert this quaternion to roll, pitch, yaw, okay? I am doing this using this specific method, Euler from quaternion, okay? But you can do this with just some mathematical operations, equations, okay? So what we do here is to extract the roll, pitch, yaw from my orientation, yeah? And then what I am going to do is to plot the roll, pitch, yaw, the 3 of them, okay? Then let's execute our program here. Let's, oh, did I not? Oh, yeah, I forgot to paste the code. Sorry. So, of course, I need to copy and paste the code to my Python script. There we go. And now we can execute it. Okay, so we have our robot here. We can open the graphical tools here to visualize the plot. There we go. Okay. Something seems a bit off here, by the way, because I'm not getting any. Okay, let me restart the simulation because maybe the simulation is affecting a little bit the system. So let me restart that. Okay. Clean Gazebo. Yeah, because the simulation has a bit of noise, and then after some time the robot moves alone, let's say, okay? Because of the forces, etc., frictions in the simulation and so on. After a bit of time of the simulation running, the robot starts moving a bit, okay? not moving, but rotating specifically. Yeah, and that can affect the system and the readings. So let me restart the simulation and then run again my program. And here I'm going to see the roll, pitch, yaw values changing over time. Okay, so on the top I have the roll is blue, the pitch is in yellow, and the yaw is in green. Okay, so we can see here the roll is 0, the pitch is 0, and the yaw is 157. Okay, so this is in radians, as you can see, not in degrees. Yeah, so 1.57 radians. Okay, and here I can see my system. So I can see the roll, pitch, and yaw, how they basically are stable at 0. Okay, here you can see some jumps, but they are a small error. These two are basically 0, and then I can see my yaw here also more or less stable. Okay, let's say. Then what I'm going to do is start rotating the robot. Okay, so let me do that. Let me start rotating my robot towards the, let's say, here. Okay, so my robot starts rotating, and then I'm going to start seeing here in the graph, yeah, how my yaw starts changing. Okay, and at some point, which is going to be here, we are going to see a jump. Okay, this is a bit laggy, by the way. There we go. Okay, so there it jumped. Yeah, approximately when it reaches 90 degrees, yeah, of orientation, it does this jump. Okay, then this is not due to gimbal lock. Okay, because gimbal lock cannot affect this system. Okay, because I can only rotate in one axis, which is yaw. Okay, but this can also be a problem. Okay, this is another problem that we also have when working with Euler angles. Yeah, you're going to see now that we have these jumps. Yeah, every time we reach this pi or minus pi. Okay, and this can be a problem also because of other reasons. Okay, but this also, of course, can be avoided using quaternions. Okay. Now, in a gimbal lock system, yeah, what we would see typically is it would happen when the pitch axis reaches 90 degrees. Okay, typically, then we would see some strange behaviors like very big jumps or misreadings, etc., either in yaw or in roll. Yeah, so this can be used to detect gimbal locks in more complex systems. Okay, again, I cannot, not here because this is not a gimbal lock. Yeah, this is a normal error that happens when working with continuous rotations with Euler angles. Okay, that can be, by the way, also avoided if you work with quaternions. Yeah, but this is an interesting system that you can use to detect gimbal locks. Okay. If you happen to have a manipulator simulation, you can test it with that, or a drone simulation, for example, an aircraft simulation. You can use this and use it to try to detect this gimbal lock and see what happens. Okay, how the system behaves and starts and becomes erratic. Yeah, when one of those singularities happen. Okay, so I wanted to show this example, which is not a gimbal lock. It's another issue that happens with Euler angles, yeah. But just to show you this tool that it's very simple and can be used in case that you have a simulation that allows you to test for a gimbal lock or to force a gimbal lock. All right. And three-axis system, but there are 3 straight axes, X, Y, Z, and 3 rotational parts, Phi, Psi, Zeta. That should total 6 degrees of freedom. Exactly. Yes. Yes, Carl. Okay, so yeah, so then here also I have left some basic operations that can be done with quaternions, like multiplying quaternions, okay, with the formulas and the corresponding Python code, so that you can use it for that. Also for normalizing a quaternion, for doing the inversion of a quaternion, and for manipulating quaternions for orientation, prediction, and correction. Okay, some very typical and operations that can be done with quaternions and that can be useful for robotic systems. Okay, then I'm going to leave it here. We have reached the hour time, so I don't want to start into too much detail here into mathematical operations. Yeah, so basically I wanted to introduce this concept of quaternion. I hope it is more clear for the ones that were a bit lost. So, are you a bit more familiar now with the concept of quaternion for the ones that didn't have any idea? Especially, I am asking. I know it can be a bit tough, okay, at the beginning, but I hope that this class has brought a bit of light about what quaternions are and why they are so important in robotics. Okay, so with this information, I encourage you to keep testing, okay? For example, the more obvious thing that I would try to do is to try to test these programs, okay, with other simulations that allow you rotations in all the axes, okay? This simulation is limited because we have a differential drive robot which only allows rotation over the z-axis, right? But I would encourage you to use, if you already have, or if not, to look for a simulation that allows you for other rotations. Yeah, for example, this kind of rotation, yeah, that our robot cannot do. But there are other robots, like I was saying, manipulators, drones, aircrafts, that allow for all these rotations. And then you can see how all these programs behave under those circumstances, okay? And try to force a gimbal lock, see how the system reacts, etc. Okay, so many things that you can do from this class. So, yeah, then one more time. Thanks everybody for attending. I hope that you enjoyed the class, that you can get some good insights from it. Thanks a lot for attending. I'm going to see all of you again next Tuesday with another class, so stay tuned for the next topic that we are going to be covering. And as always, until we see again, keep pushing your robotics learning. Bye-bye.